Okay, so we were just talking about converting to polar, right? And so we have some function, right? Some surface above this thing. And if I'm talking about the partial with respect to, so I'm doing partial z with respect to x, right? Or partial z with respect to y. And say I had some point here, right? So at that point, if I'm talking about these numbers, right? So say this is my point, a comma b. If I evaluate this at a comma b and evaluate this at a comma b, right? What do these things mean? Like these will be a number, right?
That is the slope in their respective directions at that point.
Yeah, so this is the slope in that respective direction, right? So this is the x slope, right? Like think to yourself the kind of change in z per change in x, right? And this is the y slope. So that'll be like the change in z per change in y, right? So those seem like they make sense. Like you've got a surface, right? That's the slope of the tangent line this way or that way, depending on which one you're looking at. But what in the hell do the other ones mean? So what is the partial of z with respect to r? Or the partial of z with respect to theta? What the heck do those mean?
The amount that the z value changes per unit of r.
You guys see that? So that's like change in z per change in r. Which direction does that point in?
Just out from the origin.
Yeah, good. Out from the origin, right? Wherever the heck out is.
Is that a projection that you have drawn up there? That's like
Yeah, so I've
opposite
projected
axis?
down.
Okay.
And so I'm just saying like change in x's go this way. Oops. Change in x's go that way. Change in y's go this way. Change in r's just go out from the origin. Where's it change in? So the other one's change in z per change in theta, right?
That would be kind of rotating, given a circle of the origin. Like,
Yeah, so that's like this, right? So change thetas are rotations. So that other problem, right, was a way to convert from having rectangular information to convert to out and around information. And so, of course, because you're converting from square to out and around, the formulas are a little messy, right? Because it should be complicated to go from square to around, especially. Cool? Does that make a little more sense as to what the formulas were doing? I get your question in there someplace, kind of.
If you were looking for like a change in the theta, like conceptually, how would that look? If they were asking you, would that be like an angle between two like rays almost, or?
Yeah, so if I wanted to approximate this thing, right? I'd take a couple points that are the same distance from the center. So I'd take like 2 points that are on the same distance to the origin.
You make vectors out of them?
So then I'd calculate this change in theta between them, right? And then I'd figure out how much different they are in z. And then I'd do the z difference divided by the change in theta difference, right? So z difference by angle difference. And that would tell me kind of how fast is this thing going up as I walk around it.
That's just an approximation, right?
Yeah, and of course that would just be an approximation. If I wanted an instantaneous thing, right, I would have to actually calculate the partial of z with respect to theta. And that would give me the instantaneous slope if you walk around. You guys cool with that? Keep in mind that angles in here have to be measured in what? Radians. Otherwise you have all these ginormous annoying conversion factors that you have to go through. Yes? You guys all know that about sine and cosine derivatives, right? That they have to be in radians for those formulas to work. Didn't know that?
No, I found out in California.
Yeah, so when you do d d theta of cosine theta, and you say that's minus sine theta, right?
Yeah.
This has to be in radians. It does not work in degrees. There's a conversion factor of 180 over pi that has to be in there somewhere. Well, the reason it doesn't work is when we're calculating that derivative, we draw this little picture. Like, we need a change in theta here, and we're in a unit circle, and I wrote cosine here. Yeah. So there's this distance here and this distance here, right? This one's cosine theta, cosine
Yeah.
delta theta, right? And this one's sine delta theta. And we use the fact that as delta theta goes to 0, this cosine distance goes to 1 and the sine distance goes to 0. That uses the fact that this arc length here is the same as that angle distance there. If you don't use this, it doesn't work.
That's so much
Cool.
easier conceptually than mathematically to me.
Yeah,
Like you take a stick, you bring it to the ground, and the length is gonna be what that stick's length was, and the distance from the point of the stick to the ground is gonna be nothing, because you brought that point all the way down.
yeah, that's totally true, and this is one of the places we lied to you. Because it's conceptually really easy for me to say this, and it's really actually kind of hard to get the geometry that makes this absolutely firm. It's like when I show you guys this in Calc 1 or wherever, I'm just like, yeah, sure. Like, obviously, as you crank this angle down, this arc length and that height go to the same value, and that value is 0. Right? Like, they get the same length. I need these to actually be the same length in that argument, because I have a sine h over h in there, and I'm looking for a limit h tending to 0 on this thing. So I need the ratio between those two things to go to 1. You guys all remember that from Calc 1? You believe that something like this could come out of the limit definition?
Yeah.
Okay, so I need this object to be 1 in Calc 1 land, and that only is true in radians. In degrees, this is some number that's not 1. Cool?
Where's your h on that?
On here. It's a delta theta. I don't know why I switched notations, but I did.
Okay.